Complementary Metal-Oxide-Semiconductor, CMOS. How does it function in electronics? Complementary metal-oxide-semiconductor, CMOS, is a fundamental technology used in the construction of integrated circuits, including microprocessors, memory chips, and other digital logic circuits. It is widely used due to its low power consumption, high noise immunity, and compatibility with very large-scale integration, VLSI, techniques. Here's how CMOS functions in electronics. The basic structure of a CMOS integrated circuit consists of individual MOSFETs, metal oxide semiconductor field effect transistors, arranged in a complementary fashion. Here's a breakdown of the basic components. Substrate. The substrate is typically made of silicon, upon which the MOSFETs are constructed. It can be either P-type or N-type silicon, depending on the specific requirements of the circuit. Source and drain. These are the terminals of the MOSFET through which current flows. The source is the terminal where current enters the transistor, while the drain is where it exits. Gate. The gate is the control terminal of the MOSFET. By applying a voltage to the gate, the conductivity of the channel between the source and drain can be controlled. The gate is separated from the substrate by a thin, insulating layer, usually made of silicon dioxide. Channel. The channel is the region between the source and drain terminals. Its conductivity can be modulated by the electric field generated by the voltage applied to the gate. Oxide layer. This is the insulating layer between the gate and the substrate. It is typically made of silicon dioxide, SiO2, and serves to electrically isolate the gate from the substrate. Metal layers. Metal layers are used to create interconnections between different components of the integrated circuit. They provide the pathways for electrical signals to travel between transistors, resistors, and other components. In a CMOS integrated circuit, you'll find both N-type MOSFETs, NMOS, and P-type MOSFETs, PMOS, arranged in a complementary manner. NMOS transistors are used to pull the output down to ground, logic 0, while PMOS transistors are used to pull the output up to the supply voltage, logic 1. By combining these two types of transistors, CMOS circuits can perform various logical functions efficiently while minimizing power consumption. Metal oxide semiconductor field effect transistors, MOSFETs, are semiconductor devices that are fundamental to CMOS technology and many other electronic applications. MOSFETs have several key components. Substrate. MOSFETs are typically fabricated on a silicon substrate, although other semiconductor materials may also be used. The substrate is doped to create either an N-type or P-type semiconductor material, depending on the desired characteristics of the MOSFET. Source and drain. These are the two terminals through which current flows in the MOSFET. The source is where current enters the device, while the drain is where it exits. The source and drain regions are heavily doped to facilitate the flow of charge carriers, electrons, or holes. Channel. The channel is the region between the source and drain terminals through which current flows under the control of the gate voltage. In a MOSFET, the channel can be either an electron channel, N-channel MOSFET, or a hole channel, P-channel MOSFET, depending on the doping of the substrate and the type of MOSFET. Gate. The gate is a terminal that controls the conductivity of the channel. It is separated from the channel by a thin insulating layer, typically made of silicon dioxide, SiO2. Applying a voltage to the gate creates an electric field that modulates the conductivity of the channel, allowing the MOSFET to act as a switch. Gate oxide. This is the insulating layer between the gate electrode and the channel. It prevents direct electrical contact between the gate and the channel, allowing the gate voltage to control the flow of current without causing a short circuit. Body or substrate. The body or substrate of the MOSFET is the semiconductor material upon which the source, drain, channel, and gate are built. It can be either N-type or P-type, depending on the desired characteristics of the MOSFET. MOSFETs are widely used in various electronic applications due to their high input impedance, low power consumption, fast switching speed, and compatibility with integrated circuit fabrication processes. They are essential components in digital logic circuits, amplifiers, power converters, and many other electronic devices. The operation of a metal oxide semiconductor field effect transistor, MOSFET, relies on the modulation of the conductivity of a semiconductor channel between the source and drain terminals, controlled by the voltage applied to the gate terminal. MOSFETs can be broadly classified into two types based on the doping of the semiconductor material: N-channel MOSFET NMOS, and P-channel MOSFET, PMOS. Here's how MOSFETs operate. NMOS transistor. Off-state, VGS VTH. When the voltage applied to the gate, VGS, is below the threshold voltage, VTH, the NMOS transistor is in the off state. In this state, the electric field generated by the gate voltage is not sufficient to form a conductive channel between the source and drain terminals. As a result, the NMOS transistor exhibits high resistance, effectively blocking the flow of current between the source and drain. On state, VGS VTH. When the gate voltage, VGS, exceeds the threshold voltage, VTH, the NMOS transistor enters the on state. In this state, the electric field from the gate voltage creates a conductive channel in the semiconductor material between the source and drain. Electrons flow from the source to the drain through this channel, resulting in a low resistance path and allowing current to flow between the terminals. PMOS transistor. Off-state, VGS VTH. For a PMOS transistor, the gate voltage, VGS, is typically applied negatively with respect to the source terminal. When the magnitude of the gate source voltage, VGS, exceeds the threshold voltage, VTH, the PMOS transistor is in the off state. In this state, the electric field from the gate voltage repels holes, positive charge carriers, in the semiconductor, preventing the formation of a conductive channel between the source and drain. As a result, the PMOS transistor exhibits high resistance, inhibiting the flow of current between the source and drain terminals. On state, VGS VTH. When the magnitude of the gate source voltage, VGS, falls below the threshold voltage, VTH, the PMOS transistor enters the on state. In this state, a conductive channel forms between the source and drain terminals due to the attraction of holes by the negative gate voltage. Current flows from the source to the drain through this channel, providing a low resistance path. Key points. MOSFETs operate as voltage control devices, with the gate voltage controlling the conductivity of the channel. NMOS transistors conduct when the gate voltage is higher than the threshold voltage, positive VGS, while PMOS transistors conduct when the gate voltage is lower than the threshold voltage, negative VGS. MOSFETs exhibit high input impedance, meaning they draw very little current into the gate terminal, making them suitable for use in high-frequency applications and digital circuits. Understanding the operation of MOSFETs is essential for designing and analyzing electronic circuits, especially in digital logic, amplification, and power control applications. Complementary operation refers to the behavior of complementary metal-oxide-semiconductor (CMOS) circuits, where both N-channel MOSFETs, NMOS, and P-channel MOSFETs, PMOS, are utilized in tandem to achieve efficient digital logic operations. In CMOS technology, NMOS and PMOS transistors complement each other's functions, allowing for the creation of highly efficient and low-power digital circuits. Here's how complementary operation works. Pull-up and pull-down network. CMOS logic gates typically consist of both NMOS and PMOS transistors connected in a complementary manner. The NMOS transistors act as the pull-down network, connecting the output to ground, logic 0, when they are turned on. The PMOS transistors act as the pull-up network, connecting the output to the supply voltage, logic 1, when they are turned on. Input and output logic levels. When the input to an NMOS transistor is high, logic 1, it conducts, providing a low resistance path to ground. This pulls the output voltage down to near ground potential. Conversely, when the input to a PMOS transistor is low, logic 0, it conducts, providing a low resistance path to the supply voltage. This pulls the output voltage up to near the supply voltage level. Inverter operation. The simplest CMOS logic gate is the inverter, which consists of one NMOS transistor and one PMOS transistor connected in series between the supply voltage and ground. When the input to the inverter is low, logic 0, the PMOS transistor conducts, pulling the output voltage up to the supply voltage, logic 1. When the input to the inverter is high, logic 1, the NMOS transistor conducts, pulling the output voltage down to ground, logic 0. This complementary behavior ensures that there is a direct transition between high and low logic levels without any intermediate states, resulting in efficient and robust operation. Logic gates. By combining NMOS and PMOS transistors in various configurations, CMOS technology can implement all the fundamental logic gates such as AND, OR, NAND, NOR, and XOR gates. Each gate exploits the complementary behavior of NMOS and PMOS transistors to achieve the desired logic functionality while minimizing power consumption and ensuring high noise immunity. Power efficiency. CMOS circuits offer excellent power efficiency because they draw significant current only during transitions between logic states. When a gate is static, not switching, it consumes almost no power because either the NMOS or PMOS transistors are in the off state, providing a high impedance path between the output and the power rails. Complementary operation is a cornerstone of CMOS technology, enabling the design of high-performance, low-power digital integrated circuits used in a wide range of applications, from microprocessors and memory chips to digital signal processors and other digital logic circuits. Complementary Metal-Oxide-Semiconductor (CMOS) technology utilizes both N-type MOSFETs, NMOS, and P-type MOSFETs, PMOS, in a complementary manner to implement various logic gates and circuits. Here's how CMOS logic gates and circuits are constructed. Basic CMOS inverter. The most fundamental CMOS circuit is the inverter, which performs the logical NOT operation. It consists of both NMOS and PMOS transistors connected in series between the power supply, VDD, and ground, GND, with the output taken from the junction between the transistors. NMOS transistor, connected between the output and ground. It conducts when the input is high, logic 1. PMOS transistor, connected between the output and VDD. It conducts when the input is low, logic 0. When the input is low, logic 0, the PMOS transistor is on, creating a path to VDD and pulling the output high, logic 1. Simultaneously, the NMOS transistor is off, blocking the path to ground. When the input is high, logic 1, the NMOS transistor is on, providing a path to ground and pulling the output low, logic 0, while the PMOS transistor is off. Other logic gates. CMOS logic gates such as AND, OR, and NAND can be constructed using combinations of NMOS and PMOS transistors. AND gate consists of multiple series-connected NMOS transistors and parallel-connected PMOS transistors. The output is high, logic 1, only when all inputs are high. OR gate consists of multiple parallel-connected NMOS transistors and series-connected PMOS transistors. The output is high, logic 1, when any input is high. NAND gate, essentially an inverted AND gate, consists of multiple parallel-connected NMOS transistors and series-connected PMOS transistors, followed by an inverter stage. The output is low, logic 0, only when all inputs are high. Advantages of CMOS logic. Low power consumption. CMOS logic gates consume power only during switching, reducing static power dissipation. High noise immunity. The complementary operation of NMOS and PMOS transistors minimizes susceptibility to noise and interference. High speed. CMOS technology allows for fast switching speeds, making it suitable for high-speed digital circuits. Wide voltage range. CMOS circuits can operate over a wide range of supply voltages. CMOS logic gates and circuits form the basis of modern digital integrated circuits, enabling the construction of complex systems with low power consumption and high performance. They are widely used in microprocessors, memory chips, digital signal processors, and many other electronic devices. Low power consumption is one of the key advantages of complementary metal-oxide-semiconductor (CMOS) technology, and it arises from several factors inherent to the design and operation of CMOS circuits. Factors contributing to low power consumption in CMOS. Static power dissipation. CMOS logic gates consume negligible power when they are in a static state, i.e., not switching. In the static state, one of the transistors in the complementary pair is off, creating a high impedance path between the power supply and ground. Therefore, there's almost no direct current path between the power supply and ground, leading to minimal static power dissipation. This is in contrast to other technologies like bipolar junction transistor, BJT, or NMOS alone, which draw static current even in the idle state. Dynamic power dissipation. CMOS circuits primarily consume power during switching, known as dynamic power dissipation. During switching, both NMOS and PMOS transistors momentarily conduct, creating a path between the power supply and ground. However, this path exists only momentarily during the switching transition, resulting in minimal power consumption over time. Additionally, CMOS technology allows for rapid switching transitions, minimizing the duration of power consumption during switching events. Threshold voltage control. CMOS technology allows for precise control of the threshold voltage of transistors, which influences the voltage levels at which the transistors switch. By optimizing the threshold voltage levels, CMOS circuits can achieve lower voltage swing requirements for switching, reducing power consumption. Process scaling. Advances in semiconductor fabrication technology have led to the miniaturization of CMOS transistors, resulting in lower parasitic capacitances and resistances. Smaller transistors have lower gate capacitances, enabling faster switching and reduced power consumption. Sleep modes and power gating. Modern CMOS-based devices often incorporate power management techniques such as sleep modes and power gating. During periods of inactivity, certain circuit blocks can be powered down or placed in low power states to further minimize power consumption. Applications of low-power CMOS. Battery-powered devices. CMOS technology is well suited for battery-powered devices such as smartphones, tablets, and wearables due to its low power consumption characteristics. IoT devices. Internet of Things, IoT, devices often operate on limited power sources and benefit from the low power consumption of CMOS technology. Embedded systems. Embedded systems and microcontrollers utilize CMOS technology to minimize power consumption while maintaining computational efficiency. Overall, the low power consumption of CMOS technology has made it indispensable in modern electronics, enabling the development of energy-efficient and portable devices across a wide range of applications. Complementary Metal-Oxide-Semiconductor, CMOS, technology finds widespread applications across various fields due to its versatility, low power consumption, high integration density, and compatibility with digital and analog circuits. Here are some key applications. Microprocessors and microcontrollers. CMOS technology is extensively used in the fabrication of microprocessors and microcontrollers, which serve as the computing brains in computers, smartphones, embedded systems, and IoT devices. The low power consumption of CMOS technology makes it ideal for battery-powered devices and portable electronics. Memory chips. CMOS-based memory chips, such as static random access memory, SRAM, and flash memory, are widely used in computers, smartphones, digital cameras, and other electronic devices for data storage. The high integration density of CMOS technology allows for the fabrication of memory chips with large storage capacities. Digital signal processors, DSPs. DSPs are specialized microprocessors designed to efficiently process digital signals in applications such as audio processing, image processing, telecommunications, and multimedia. CMOS technology is used to manufacture DSP chips, enabling high-speed signal processing with low power consumption. Analog and mixed signal circuits. CMOS technology is also employed in the design and fabrication of analog and mixed signal circuits, including analog-to-digital converters, ADCs, digital-to-analog converters, DACs, amplifiers, filters, and sensor interfaces. CMOS technology offers advantages such as low noise, high linearity, and compatibility with digital circuits, making it suitable for mixed signal integration. Wireless communication systems. CMOS technology is used in the development of wireless communication systems, including cellular networks, Wi-Fi, Bluetooth, and RF transceivers. The integration of CMOS-based RF front-end circuits enables compact, low-power wireless devices with advanced features. Imaging sensors. CMOS image sensors are widely employed in digital cameras, smartphones, surveillance cameras, medical imaging devices, and automotive applications. CMOS image sensors offer advantages such as low power consumption, high resolution, fast readout speeds, and integration with image processing functions. Power management ICs. CMOS technology is used in the fabrication of power management ICs, MICs, for regulating voltage, current, and power consumption in electronic systems. MICs play a crucial role in optimizing energy efficiency, extending battery life, and protecting electronic components from overvoltage and overcurrent conditions. Sensor networks and IoT devices. CMOS technology enables the integration of sensors, microcontrollers, and wireless communication modules in IoT devices and sensor networks. IoT applications include smart home devices, industrial automation, environmental monitoring, healthcare systems, and agricultural sensors. Overall, CMOS technology serves as the foundation for modern electronic systems, enabling the development of advanced devices and applications across diverse industries. Its scalability, low cost, and energy efficiency continue to drive innovation in electronics. Overall, CMOS technology forms the backbone of modern digital electronics, enabling the construction of complex integrated circuits with high performance and efficiency.